それじゃあ始めたいと思います。what I want to give you is that now I consider the initial boundary value problem in some abstract form. G, positive time, and then initial condition. Then my approach is to consider the corresponding resolvent problem. Okay, now and I want to repeat the some assumption and so on. So X and Y and Z are three Banach spaces. And operator A, main operator, is bounded linear operator from X to Y. And the boundary condition B is also bounded linear operator to Y to Z, intermediate space Z, and also Z to Y. So the typical, I already maybe gave you, but typical example is Laplace operator, and then B, for example, B is Neumann operator, Labra. And okay, right. And so we consider the Neumann problem for the heat equation. On boundary. This is in omega. Sorry, and it's on boundary for any t. And initial data. So the classical situation is that you take X is H2 to omega, and Y, underlying space Y omega, and the intermediate space Z. This is one of the typical situation in my mind. So, okay. It's okay. The parameter lambda is just corresponding to the time derivative dt, and lambda ranged usually, yeah. So parabolic sector, complex number, except for the origin, because we want to define the argument lambda. It's less than pi minus epsilon. lambda is greater than lambda naught. So the argument, the restriction for the argument lambda with pi minus epsilon is maybe Japanese school. When I was young, I learned this way, but recently I have some of the colleagues in Germany. Germany is not writing this way. They write, how to say, some of the theta instead of pi minus epsilon. But so epsilon is some number, what that means. Number. So the parabolic sector is there is epsilon is this way. You take we consider this is side of our sector. So in principle, we consider the parabolic problem and then maximal regularity. Okay, then the main assumption is our following. I think already I gave you the notion of R boundedness and Y's Fourier multiplier theorem. But maybe to understand my assumption, it's much better to give you again Y's theorem. Okay, so one of the main tool is that we are considered operator value the Fourier multipliers. So meaning that MC is L infinity function defined on R except for origin. And for each M, this is bounded to linear operator from X to Y. And denote the set of all bounded linear operator from X to Y. Okay. Then we consider operator value the Fourier multiplier TMF. Definition is first we write the Fourier transform for F, and then this is X valued function on the Fourier transform, and then you multiply the map from X to Y. Therefore, this is Y valued, and then you must transform. So this is a multiplier, operator valued multiplier. Okay. Then Y's theorem. Proof is very clear. So if you are interested in, then I recommend you to read his papers. Of course, you have to know something real analysis, but anyway, proof is very clear. Mathematical analysis, mathematician analysis. Page. And then the theorem is the statement is the following: let X and Y be two UMD Banach space spaces. And MC C1 are except 0. And then value is operator, bounded linear operator from x1. So each xi, mxi is bounded linear operator from xy, and mxi is differentiable once in xi, and then m prime xi also belongs to this for each xi. C satisfy multiplier condition. I forgot to define this norm. I give after this seven. I give it anyway. So MC, you consider operator family. So for each xi, m of xi is a bounded linear operator from xy. Therefore, xi move here. So this set is the operator family of Lxy. So R bound of this operator family is bounded, some RB, and also differentiation of m prime xi with respect to xi times xi is a bounded linear operator, R bounded linear operator from x to y. Then Tm is bounded linear operator from R to LP. Then for any p exponent p except for 1 and infinity, it's a usual assumption for p of multiplier theorem or the Fourier transform. Fourier transform is the exception for p for 1 and infinity. For any p between 1 and infinity, so Tm is a bounded linear operator from LP X to LP Ry. And Tm F R is some constant Cp Rb R X. This is the whole statement of Y's operator bounded Fourier multiplier theory. So RV is this RV. Therefore, you can calculate a bound. This is important for application to the PDE. We have to calculate this RB for the concrete problem. So where CP is some absolute constant. Essentially depending on P. So you don't care about CP, but this is important. And then later, maybe I also want to give you some how to prove the R boundedness for the Stokes operators in the half space or the whole space. If you know this, then maybe you can apply your program. Okay, anyway, so this is this abstract theory, but this theorem is very useful for the application to the PDE, I think. And then the R bound is the following. Therefore, if you remember that someone indicated to me after my lecture last time, I forgot to give the norm. So and also for example, FLP R X means that the FLP F is a function valued in X, therefore it takes X norm. And then this is a positive scalar function with respect to time t and the power p, and then dt r one over p. This is a norm of LP Rx, so X valued LP function. So this is finite. So usually you know that the usual LP function, but instead of usual absolute value, you take X norm because of the F is a function from R to X. So this is sorry, this is already. I think you already know very well, but just. Okay, and then also R bound. R bound is that the T is X to Y. R bounded. Any integer n, any finite number of Fj, and also for any finite number of operator Pj. R bounded, so T is Rj. You consider this linear combination, and then you take Y norm and some P R, sorry, 0, 1. This let's see some constancy. 0, 1. Sorry. The step is again, it's not so exact. I forget. Du here. Maybe last time I gave you the exact statement, so therefore, could you please see the note last time? But then my purpose is I forgot the definition of R, this norm R. Therefore, so in this case, R and XY, this operator family is maybe you understand. You not see. So this constant C and also P is exists such that for any is for any n and finite n numbers of Fj and also the Tj, then you consider this linear combination, and then you take the LP norm with respect to U. Then this is estimated by this one. So Rj of U is a Rademacher functions, which its values is -1 or 1. Yeah, so I think please details, please see that just the note last time, but then I want to say you again. So I forgot the definition. This is just infinite moment C. So okay, and P, if you can find one P, then for any P, this hold also. So P is not so important, but she is, so essentially C. Okay, so she is also maybe, depends on P, but maybe later I will give you some the R boundaries of some. Okay, later how to prove the existence R bounded of some operators, which are really important operators to represent the solution to the Stokes equations. Okay, but it's later. Then, so today's main assumption is following. Is there exists some lambda 0? And alpha. Concrete problem alpha equals 1/2. And operator family is lambda. The holomorphic function defined on lambda 0. Value is linear bounded linear operator from y cross z to x. Sorry. Such that one for any lambda and G y cross z. Now, sorry, now we'll consider this resolvent problem. Maybe later I write exactly, but now I consider this resolvent problem. V is equal to S lambda if lambda alpha G plus G is a unique solution of equations lambda P minus AB S AB G. maybe a little bit complicated to understand. But for example, y s lambda is for each lambda bounded linear operator from y cross z. Here is f I g g to x b, not directly f g to b. No, no, it's a. If you know some of the boundary value problem, then okay, maybe later. Or sorry, maybe I mistake some orders. But okay, anyway. So this S lambda operator S of lambda is correspond the F and lambda times alpha G this triple to solution B. Okay. And the second, there exists some RB such that this is R bounded L of y cross z to x of this tau d tau s lambda and the moreover lambda times this lambda. This is also R bounded. This is additional assumption of this. I explain the meaning. Anyway, this is assumption. So now, okay. So we consider this resolvent problem with non-homogeneous boundary condition. Then we assume that the existence of the R-bounded solution operators is lambda. So for each lambda, this is a bounded linear operator from y cross z to x. So this f is y, and the lambda alpha g is y, and g is z. The solution is in x. And moreover, so this operator S lambda and t tau t dtl 0 is 1. T 1 is of course d. So if you remember that the y theorem, then S lambda itself and tau, and lambda is tau plus I, gamma plus I tau. And this tau is a Fourier variables. And gamma is some kind of the parameter. And also, we consider the lambda times S lambda. This is corresponding to the time derivatives. The time derivative. So the lambda times S lambda is also R bounded. But that case is R bounded is in Y, not X. This is assumption. Then why I assume this historically, the historical background is the following. Okay. The historical background is much better. It was better to explain your historical background and then give that this assumption. Maybe order is, reverse. But so something. I don't know nowadays, but when I was young, so basic which Russian people, so Russian mathematician mainly. When I was young, it's more communist party country, so we are separated. But mathematics is over mathematical information about the mathematics. Also, they write their mathematics with Russian. So usually we cannot read. I cannot read the Russian papers. But there is some of the translation. There are Russian mathematical survey. And usually when I was young, I learned many of papers that appeared in the Russian mathematical surveys. It's a very now the people also the Russian people also write their papers with English, but 90-60 days or 90-70 days, the different situations. Anyway, so maybe more people consider the resolvent problem, the same resolvent problem. And what they prove is that usually just they prove the existence of solution U, and then they prove lambda times U Y plus UX is less than constant times F plus lambda alpha G Y Y. This kind of estimate. So this is parameter elliptic problem. So certain moment, it was popular to prove this kind of estimate for the general elliptic operators with parameter lambda on the general bounded conditions. Sorry, so my friend is, I forgot one name, the Denk. Wrote a book. Not recently, 10 years ago, Robert wrote a book. So, but anyway, so as far as I know, that the Bishik and Agranovich and so on is started to study the parameter elliptic problem. But before, of course, the many important points. Sorry, one of the typical problem is the generation of analytic semi-group. So also we consider this zero. And then if you know this kind of estimate, Fy lambda, then generate C0 continuous analytic semi-group T. This is Professor Fujita told me that maybe not only me. Fujita told that there was some of the competition of the Russian school, the name of Russian school, and Fujita Kato, Japanese. So some competition of to construct general theory of the generation of analytic continuous analytic semi-group and the application to the Navier-Stokes equation. This is 50 days or 60 days. It's one of the main topics for analysis. And then so this is important estimate for the parameter elliptic operate equations, but with zero. Then the generalization is a G boundary, non-homogeneous boundary conditions. Then they find, so here is some lambda G times G. It's usually 1/2, but okay, some R. So this is mainly they developed 70 days, even the Denk robot continue the study of these peoples. So. And then, but I think maybe before appearing the R-bounded solution, Weiss theorem, maybe start the studies, just stop this one. But then now, after Weiss theorem, really we can apply this kind of estimate to generation of to find the unique solution to the time-dependent problem with non-homogeneous boundary condition. But unfortunately, not enough to the boundedness. What I found is that we need R-boundedness, right? So it's not enough, this estimate. Instead of this estimate, we assume that the R-bound estimate for solution operators or solution to this. So this is some kind of history. So for example, so if you remember that the definition of R-boundedness, then you take, so if this assumption is satisfied, then if you remember that the definition of R-boundedness, and you take n equal 1, then actually you get to this estimate, right? Meaning is that and if you n equal 1, then you get this estimate. You get this one. But R-bound require, for example, even lambda 1 or lambda 1 minus u minus lambda 2 u or f, okay. So maybe very much complicated. I don't give you. N equal 1 case, you get this estimate. But the R-boundedness require u for any n. Therefore, it's much more complicated to prove. to prove the existence of unbounded solution operators. But anyway, today I want to give you some abstract structure. Then theorem is the following. Now we consider the evolution equation again. Then, as you know well, that this equation divided into two parts because this is a linear operator. Therefore, dt minus AB equal F, dB equal to G for AT, and 2 and 3 is dtw, then 0, 0, and W E is equal to, maybe from this point, then U0 minus B T equals 0. Then divide this problem into two parts. So then U is equal to B plus W. Okay. Then the theorem. First, we consider the second problem. Sure. Yeah. Gamma 0, lambda 0 is the constant appearing in assumption. That's not. Right, remember F e to the minus gamma t is LP on Y, and e to the minus gamma t G LP R Z intersection H alpha P R Z R1. Sorry, I will give you the definition of this space later. But maybe you can imagine what is H alpha P. So right hand side F and G satisfy this condition, regulated condition. Then problem 2 solution. B with H1 E Y intersect LP of X and satisfying S3 e to the minus gamma T. Sorry, I forgot this, the gamma or any gamma 0. So excuse me. And e to the minus gamma T PTU LP B, sorry, B LP R Y because of the dt plus e to the minus gamma T E LP R X is less than sometimes e to the minus gamma T if lambda alpha G this is LP R Y cross Z. In other words, it's maybe if you are not so familiar with this notation, then it is the normal for the vector valued function is f r y plus e to the minus gamma t the alpha g p r y and e to the minus gamma t g p r z. This is maybe I think you know very well, but it's the definition of vector valued known for the vector valued functions. And lambda alpha g is just lambda alpha and Laplace transform g and the Laplace inverse transform. And maybe I don't give you the definition of the Laplace transform. I will give you soon. And then, sorry, a lot of notations. And then H alpha P or Y is F LP Y and F H alpha finite and F H alpha normal definition is 1 plus C square over 2 and Fourier transform of F C and then Fourier inverse transform. We take LP now. This is definition. hope that you're familiar with Fourier analysis. This is usual Fourier analysis. Okay. And sorry, a lot of notations. And what? And the Laplace transform. The main tool, one of the main tools my talk is Laplace transformation with respect to time. So L of f lambda is equal to integration on r e to the minus lambda t ft. Lambda gamma plus I tau. So this is e to the minus gamma t is, if you write e to the minus gamma t, if you I tau t, for this is a Fourier transform. Therefore, it's equal e to the minus gamma t ft. If you write in this way, then you understand the relationship with Laplace transform and Fourier transform. Namely, this is Fourier transform of e to the minus gamma t ft. And Laplace inverse transform G is 2 pi I, also R to the gamma lambda t, sorry, t, d lambda, d lambda. Here also gamma is just on the real line, but gamma plus I tau. The integration is lambda is with respect to tau. So it's more of, if you write, e to the gamma t, e to the I tau t, d gamma plus I tau, and then integration on tau, so deta. So I deta, I tau. So integration is on this value is I tau. So d lambda, I deta. So I is the cancel here. So this is definition of Laplace inverse transformation. So you take this is outside because it's independent of integration. Therefore, we can write t to the gamma t for the inverse transform of G plus I tau, or I don't know what is a good notation. I don't know where, but so this is Laplace inverse transform. so it's just if you just shift the Fourier transform with respect to gamma. So Fourier transform is just this over here, IR. So this is Fourier transform. Then you shift gamma. This is Laplace. So please remember this relationship L over F is defined by this, and L inverse G is defined by e to the gamma t times this Fourier transform. This is a very fundamental relationship where if you use the Fourier analysis, the PDE, you understand that from my lectures. Okay, then how to prove it? It's easy. So now we consider problem 1. And P G for all t. Then apply Laplace transform. So, and then, as you know, that the dtu Laplace transform is lambda times u Laplace transform u. So for simplicity, write the hat. And of course, we assume that A is a linear bounded operator. Therefore, Laplace transform of AU is independent of time variable. Therefore, this is closed graph theory. You can write it in this way. And B also. Well, you get 2 lambda u hat minus a u hat and b u hat g hat. And then by assumption, your hat is written S lambda and F and lambda alpha G and G. If this is S lambda, Fourier transform of e to the minus gamma t f lambda alpha g. You can write in this way. Then, of course, U is how to define the U is defined by Laplace inverse transform of U hat. So it's gamma t Fourier transform of S lambda of this Fourier transform e to the minus gamma t alpha g so Fourier inverse. Sorry. Plus gamma t. Fourier inverse transform. So this is a solution formula. If you assume that the existence of a solution operator S of lambda, then this is a solution formula for general parabolic or general boundary value the initial boundary value problem, non-homogeneous boundary value problem. So you can write solution in this way. And moreover, applying, you can apply. And then if you write this is e to the minus gamma t is equal to u inverse so lambda also gamma plus I tau, and then f e to the minus gamma t f lambda g. If you write in this way, and then this is Fourier transform of this function, then apply this operators, operator value, the multiplier, and then Fourier inverse transform. So you can apply the Weiss theorem. The Weiss theorem. And you have e to the minus gamma tu LPR x is less than, of course, this is R bound. Therefore, CP RB e to the minus gamma t of F lambda alpha G R. Here is Y cross. This is a direct application to the Weiss theorem. And moreover, if you remember that dtu is equal to, you apply dtu, then here is lambda inverse. This is, so you repeat this one. This is lambda. This is a representation formula for the time derivative of u. So you get e to the minus gamma t dtu is equal to Fourier inverse transform of lambda s lambda apply to f Fourier transform e to the minus gamma t g yes. And our assumption is lambda s lambdas are bounded solution, are bounded operator from y cross z to y now. Therefore you get, again, you apply the y theorem. Then you apply the y theorem into the minus gamma t dtu. Now r to y less than constant times e to the minus gamma t f So this is a proof. This is the end of proof. So in some sense, I give you how to prove the existence theorem for the time evolution equation. But my theory, or what I want to tell you is that so that we are concentrate on the existence of R bounded solution operator or the resolvent problem. So what I want to tell you is that once you proving the existence of R-bounded solution operator, you can immediately show that the existence of a solution to the evolution equation having the maximum regularity estimate. Yeah. So the point is that the main point is that the proof of the R-bounded existence of R-bounded solution operator. Then maybe why? Okay, so the second step is also second. Today, maybe time is almost over the whole. But then the second is historically, it's more initial value problem. So this is if so the well-known cell is the following. So if operator A has sorry. Now of course So to consider this problem, usually one of the way is to consider the resolvent problem. Now here is and then okay, so operator, so the domain of operator is u x, and then u is equal to then operator A is considered as the on D. So usual problem is written in a lambda u minus AU. And forget about the boundary condition. So this is analytic semigroup setting. So you consider operator A, just definition of operator A on. So A is operator defined on D. So boundary condition is included here. So in this way, you forget this. Just you consider this operator, right? So this is the semi-group setting. And then what is important is that so okay, so there are some epsilon. Then the lambda is so belongs to here. Then you can show the lambda I minus A. Another one is then lambda is in resolvent set of A. Resolvent set means that lambda I minus A inverse exists. Moreover, this is from, of course, Y to Y. If you consider this operator from Y to Y, then this is estimated by 1 to lambda. Then you know that the A generates A continuous analytic semigroup. So maybe I don't know if the first, but when I gave a lecture, and this is theorem is here. There is my university. Even Yoshida, Phillips Miyagera theory. I call it's a generation of analytic semigroup. So and then the solution is if you put zero. Excuse. No, sorry. This is dt because I put here initial data. So if you apply T of T, this analytic semigroup I group to the initial data, then you give so then U is a unique solution to this equation. This is a unique solution to this. Sorry, I really confused. Now here is zero. Excuse me. Okay, so anyway, first you consider this resolvent problem with zero boundary condition. And then D is defined in this way. So all the U is the element of X, and then B equals 0. And then A, you consider operator A is defined on D. So meaning is that A is map from AU to Y. AU is in Y, but then, okay, so you consider this, but without this one. So maybe this is good. This F, only this. So, but this is including, U equals 0 is including. Oh, that's, excuse me, maybe you know. Then the A generates, A has, if A satisfies this estimate, so I mean, lambda is here, then usually you can show that the existence of inverse operator, lambda I minus A. Another words is lambda belongs to the resolvent of A. The moreover, this estimate satisfies. So this inverse is estimated by C times some constant C times 1 over lambda. Then A generates a continuous analytic semi-group, maybe say on Y. And then if you put U, if you define the U is equal to T of T U0, then the U satisfies this, and then initial condition U0. So T is positive. But this is including definition of A operator A is including B equals 0 on the boundary. Moreover, estimate is the following. So UT is Y norm, sometimes constant times gamma 0T 0. But analyticity tells you that DTUT Y is constant times e to minus 1 e to gamma 0 T 0 for positive T. This is analyticity of semi-group T of T. Okay, and then of course the AU also estimated by using this. But the question is usually if you consider the non-homogeneous condition, I mean. Then because the situation is in L infinity in time, so maybe if we want to solve this problem, right, remember F, then one of the assumptions is it's a Herder continuous, 1 plus alpha. Then, of course, U is in DTU is in H1 plus alpha. Herder, sorry, H alpha. Herder continuous. H alpha is meaning is that SP minus Fs operator Y E minus S alpha is also bounded. So Herder continuous. So F is Herder continuous with exponent alpha. Then DTU is also belongs to the same space. So you need this regulate when if you consider this problem in L infinity in time space. Okay, this kind of situation also happened in, for example, if you consider Laplace operator, Laplace equation, F. And then you cannot solve this when you L infinity. There's some counterexample. But if you consider it's a bit Herder continuous, usually how to write, not L infinity. Okay, so some Herder continuous space gain alpha. Now, alpha positive. This is well known. Meaning that you cannot solve for any infinity function, just bounded function if you put here. And then usually you cannot solve this. But if you assume the sum of the regularity of the slight regularity, delta continuity, then you can solve. So it's not, so this is not maximal regularity. I mean, this situation happen for even for this kind of evolution equations. Why we consider the maximal regularity? Now, but if you know that maximal regularity, then our theorem F is LP, in some sense LP in Y. Of course, we need weight, but Y. Then the solution belongs to the U, H2 P, Y. Or even maybe better to write ETU is LP or so this is our theorem. Already you know this one. If the solution operator, the R-bounded solution operator exists, then you can say this one. So what is the difference is we don't assume that any regularity for F, but we consider LP. So if P is just between an infinity. So this is this kind of fact is important when you want to solve some of the Navier-Stokes equation, nonlinear problem. So this assumption is you assume some kind of regularity in time, alpha regularity in time. But this also, if you consider the boundary value problem, then this requires use some of the more compatibility conditions for the initial data. It's not so good for to solve the nonlinear problem. Therefore, so far it is worthwhile. I mean, so LP, this kind of maximal regularity is more important to solve the minimal regularity of the solution to the Navier-Stokes equation, for example, or not only Navier-Stokes, MHD, or any kind of parabolic nonlinear problem. Maybe so far, it's LP theory is good. So far, I don't know the futures, but now this is why do we are now really much want to study LP maximal regularity theory. It's main reason is the applications. Okay, thank you very much. Maybe next week we continue this kind of things.